Hello and welcome to Lecture 4 of Foundations of Artificial Intelligence. Today I'm going to be covering representation in propositional logic. In our previous lecture on AI concepts, we covered the following topics. We talked about knowledge representation, including formal representation versus natural language. We talked about syntax and mapping with semantics. And we tried to answer the question, what makes a knowledge representation effective? We also talked about the basics of logic, including arguments and what makes them valid or sound. We looked closely at an early form of formal logic called syllogistic logic. We learned about the syllogism, and we learned how to do the star test of validity. We also gave an overview of reasoning, and learned the difference between deductive, inductive, and abductive reasoning. Today's lecture includes answering the question, what is propositional logic? We'll talk about propositional language, propositional truth, equivalence, and logical calculation. First off, why do we care about propositional logic? This topic provides the skills needed to more easily work with, manipulate, and reason with more complex knowledge and tasks. Effectively today, we're going to learn the calculus skills needed for reasoning. Let's briefly revisit syllogistic logic. Syllogistic logic, as you might recall, is a system of reasoning used by the ancient Greeks. Part of it examines the fundamental principles of logical transference. In other words, if A equals B and B equals C, then A equals C. Propositional logic builds from syllogistic logic. Alright, so what is propositional logic? First off, let's define a proposition. It's a declarative statement that's either true or false, but not both. A proposition can also be referred to as a formula. An atomic proposition is the most basic form of proposition. In other words, it's a fact where the truth or falsity of that fact doesn't depend on any other propositions. Here are some examples of propositions. The statement 1 plus 1 is 2 has a value of true. The statement 1 plus 1 is greater than 3 has a value of false. Allison likes patient care, we'll assume that's true. And Ryan has an MD, that's not true. So what are some incorrect examples of propositions? Well, for one, the formula 1 plus 1 is greater than x. We can't determine its truth, so this is not a proposition. The statement, what a great book, is really an opinion and doesn't have a truth value. Similarly, the statement, is your car red, is a question and again doesn't have a truth value. Now let's define a paradox. It's a statement that cannot be assigned a truth value. Therefore, a paradox cannot be a proposition. Here's an example, also referred to as the liar paradox. This statement is false. Think about that statement for a second and you'll realize that it can neither be true or false. So now let's define propositional logic. First off, it's a formal modern logic. It's also referred to as Boolean logic, symbolic logic, propositional calculus, statement logic, or zeroth order logic. As mentioned, it relies on the principles established by syllogistic logic. Propositional logic is concerned with truth and falsehood. More specifically, how truth values extend through a series of propositions. For example, let's check out this statement. Ryan is the course director, and Ryan is a magician. Both of these statements are propositions with their own truth values. In this case, the first is true and the second is false. When put together, this statement has to be false because I am not both the course director and a magician. Propositional logic allows us to build up more complex statements, also called sentences, by combining propositions with logical connectives. This is the foundation of the syntax of propositional logic. Now let's learn about the propositional language itself, which includes its syntax and semantics. First, let's learn about variables in propositional language. To formalize atomic propositions, we use simple symbols. These are also known as propositional constants. These symbols inherit the same truth values as the statements. There are a couple reserved constants. For example, F is a symbol that always represents false, and T is a symbol that is always true. Using the examples from earlier, we're going to assign each one of these propositions a symbol to more easily represent it. These symbols inherit the truth values of the original propositional statements. A propositional signature is a set of propositional constants. Now let's learn about connectives. These are also called logical operators. Down here we see the full set of connectives. The first connective is conjunction and can be represented by any of these symbols. The preferred symbol that we'll rely on in this course is given in red for each. The conjunction connective basically means and. The disjunction connective means or. The negation connective means not. The implication connective means if, then. And it connects two propositional constants. Lastly, there's biconditional. which looks like an equals but is different. This means if and only if. Now let's define a propositional sentence. This is a statement obtained by using connectives to combine members of the propositional signature. Here's an example over here on the far right. We have two propositional constants connected by the conjunction, or the and connective. So this statement means P and Q. A propositional sentence can also combine a compound expression formed from members of the propositional signature. Basically, it's a more complex combination. Here we have an atomic proposition combined with a more complex proposition. This reads S or P and Q. Now let's learn about truth tables. These describe the behavior of a proposition under all possible interpretations of the atomic propositions included. That sounds complex, but this is actually pretty easy in the end. Recall here that when we're talking about atomic propositions, we're talking about the simplest true-false propositions that are represented by propositional constants, in this example, P and Q. The length of a truth table is based on the number of atomic propositions that we're considering. Given n different atomic propositions, a truth table can have 2 to the n different lines in the truth table. This is because each atomic proposition can take one of two values, true or false. So let's walk through an example. Here we have two atomic propositions. Finn likes cakes is represented with a P, and Finn eats cakes is represented with a Q. Both atomic propositions go into our truth table, and we consider every combination of true-false that pair of propositions can have. As we'll see later, we can add other propositions based on those atomic propositions to the table to work out their truthfulness. For example, this represents not P. So whenever we see true for P, it'll be false here, and vice versa. We'll also use this truth table idea to better understand connectives in the following slides. First, let's talk a little more about the connective conjunction, or and. The way truth is handled here is that something is true only when both are true. Let's use our example from before with P and Q, and we can look at our truth table to see the results of using the and. In this case, the only time P and Q is true is when both P and Q are true. Otherwise, it's false. We can think about this visually with a Venn diagram. We have two circles that represent P and Q, and the conjunction P and Q represents this middle section that's highlighted. The red color is used to describe where truth occurs. Now let's talk about disjunction, otherwise known as or. This is represented by this symbol. When using or, the statement is false only when both propositions are false. Here's the truth table for disjunction. Here we can see that the only time P or Q is false is when both P and Q are false. Otherwise, P or Q is true. This is because you only need at least one true in either column here. Here's the Venn diagram describing truthfulness using or. If either P or Q is true, then P or Q is also true. Now let's discuss negation, or not, represented by this symbol. Unlike the other two connectives we've talked about so far, not only applies to one proposition at a time. Not basically inverses truth. Here's our truth table. When we have false for P, it becomes true when we have not P, and vice versa. Next, let's talk about the slightly more complicated connective called implication. Implication basically means if something, then something. It's represented by this arrow to the right. The implication is true whenever P is false or Q is true. In other words, P implies Q. Here's the truth table. So the description of implication assumes that P is on the left. So P implies Q is true whenever P is false or Q is true. Therefore, the only situation in which P implies Q is false is when P is true and Q is false. Here's the Venn diagram for implication. Basically, the only time this statement is false is when only P is true. Let's dig into implications a little bit more and think about what it means to be sufficient and necessary conditions. When you have P implies Q, P is called a sufficient condition for Q, but Q is a necessary condition for P. Let's look at a natural language example of this to see if it makes more sense. Here we have the statement, being Japanese is a sufficient condition for being Asian. In other words, if someone is Japanese, then he or she will be an Asian. However, being Asian is a necessary condition for being Japanese. Therefore, if someone is not Asian, he or she could not be Japanese. Now let's discuss converse, contrapositive, and inverse. From the implication if P then Q, we can describe new conditional statements. If we have the statement if Q then P, this is called the converse. The statement if not P then not Q is called the contrapositive. And the statement if not Q then not P is called the inverse. Here's an example starting with an original implication. If it is snowing, then I will not go to school. The converse would be if I do not go to school, then it is snowing. The contrapositive would be if it is not snowing, then I will go to school. And lastly, the inverse is if I go to school, then it is not snowing. As I go through these slides, feel free to pause and think about some of these examples along the way. Lastly, let's look at the biconditional connective. Again, this means if and only if, and is represented by this symbol. The biconditional is true if P and Q are both either true or false at the same time. Here's the truth table. Notice that P biconditional Q is only true if P and Q are both false, and only when they're both true, but not when they're different. You can think of this statement as if Finn likes cakes, then Finn eats cakes, and vice versa. You can also think of this as an implication that goes both ways. Here's the Venn diagram describing the biconditional. Here something is only not true when only P is true or only Q is true. Now let's get into the grammar of propositional language. First, let's define an abstract proposition. These are more general than atomic propositions. They can be any syntactically correct proposition, otherwise known as a well-formed formula. Here are some examples. You can nest complex propositions as deeply as needed, but parentheses might be needed for grouping. Here are some examples of incorrect abstract proposition. For instance, an atomic proposition with the and connector alone, two implications and an atomic proposition, and the not connective being combined with two propositions. In general, you want to omit as many parentheses as possible, but without causing ambiguity, much like we do in algebra. As we'll reiterate in a minute, negation has the highest priority. Here are some examples of simplifying abstract propositions without losing their original meaning. In this example, we can sequentially remove the parentheses without losing the original meaning. The same is true in this example. However, it's not true in this final example because the negation operator has the highest priority. Therefore, these parentheses cannot be removed without changing the meaning of the expression. Here's a summary of the precedence of logical operators. This is similar to what you might need to worry about in mathematics. As I said before, the negation operator has the highest precedence. This is followed by and, or, implication, and biconditional. Here's another example for you to ponder. Now let's dive into propositional truth. Here we revisit and learn to compute truth tables. Let's say we want to compute the truth table for this proposition. First, we include all the atomic propositions found within it. In this case, P, Q, and R. We then start adding propositions based on the rules of precedence. So in this case, negation R has the highest precedent, and so we add it to the truth table. Next highest precedent goes to P or Q. Lastly, we combine these two expressions together using the implication. We can assign truth values to these original atomic propositions easily. Basically, they're just every combination of true and false possible. In this case, there are 2 to the 3 possible rows, or combinations of true and false. Now we can move right in the truth table, filling in the rest of the truth values, if they weren't already filled in. For example, for R, we can fill in negate R by just flipping truth values along the way. For P or Q, we refer back to the atomic propositions and ask, is there at least a true in one of these two cells? Notice the only time we see a false is when both P and Q are false. Lastly, we can fill in the truth values for the final proposition by relying on the rules of the implication truth table that we learned earlier. Basically, we'll only get a false for this proposition if there's a true value for the first part of the proposition and a false value for the second. We can now calculate truth values for all of these. Here, for the first part of the implication, we have a true value, followed by a false value for the negate R in the second part of the implication. Because of this, this cell value gets a false. We can now assign a false to any time we see a false here and a truth there. Here's an example, so we see a false. Here's another example, so we get a false, and that's it. The rest of these values become true. Now let's talk about interpreting truth tables. Every row in a truth table is a possible interpretation, otherwise known as a model. Interpretations are basically possible worlds. Finding the possible truth values of the constituent propositions gives us meaning of the sentence. The term propositional interpretation refers to truth mapping of propositional constants, such as these atomic propositions. In other words, is it snowing? Is that true or false? There is a hurricane, true or false? Or there is school today, true or false? Sequential interpretation is truth mapping of propositional sentences, such as the example we just gave in the last slide. Let's examine a single interpretation or model of this truth table. This line says the following: it is not snowing, but there is a hurricane, therefore there is no school today. We could also represent these interpretations or models with a tree. The formula here is our new proposition. The model is our interpretation. Similar to the truth table, we can start with our lowest leaves of the tree being our atomic propositions and their values of truthfulness. So in this model we're exploring, we're saying that A is true, B is true, and C is not. We can use this tree to examine truthfulness as it goes up to our initial formula. So our first leaf starts with true, but is negated and becomes false. Combining these with the AND gives us false because they're not both true. Lastly, we ask if these two statements are equivalent, which they are because they're both false, yielding a final truth value of true. Now let's describe some properties of abstract propositions. First, we have valid propositions, also known as tautologies. Here, every interpretation is satisfied. In other words, it's true. Then we have contingent propositions. This means that some interpretations satisfy it, but others do not. Lastly, we have unsatisfiable, which means that no interpretations are satisfied or true. A tautology is an abstract proposition that is always true. In other words, the sentence, heads I win, tails you lose, which always has to be true. Another example is, this course is easy, or this course is not easy, which also, by necessity, always has to be true. Here we represent that statement with symbols. P, or not P, is equivalent to always true. If we look at an example of a tautology in a truth table, we'll notice that every single row, otherwise known as an interpretation or model, is always true, or the number 1. On the other hand, a contradiction is an abstract proposition that is always false. For example, the statement, this course is easy and this course is not easy. Since both things can't be true at the same time, this statement is always false, and we can represent it with the symbols here. P and not P is equivalent to false, always. As expected, when we look at the truth table, all interpretations or models are always 0 for the proposition that is a contradiction. Lastly, we define contingency. This is an abstract proposition that is not a tautology nor a contradiction. Here are some basic examples. Next, let's move on to the concept of equivalence. Here's where you'll need to dust off your algebra skills. Equivalent propositions are abstract propositions with identical columns in a truth table and are said to be equivalent. Another way of thinking about them is that they have matching truth values in every model or every interpretation. By definition, one tautology is always equivalent to another, and any contradiction is always equivalent to another. Here's an example of two contingencies that we can see are equivalent based on the truth table. They're equivalent because for every model, the same truth value can be observed. Let's look at some natural language examples of equivalent propositions. In the first case, Alice is not married, but Bob is not single. This is equivalent to the statement, Bob is not single and Alice is not married. Merely the order has been changed. Yet another equivalent statement to these is, neither Bob is single nor Alice is married, represented slightly differently here. All three of these statements are in fact equivalent, and we can see this using the truth table, where all three interpretations give you the same truth values for all three of these propositions. Before we move on, let me describe some extended notation that we're going to use for convenience throughout the next section. Whenever two propositions are equivalent, we'll write them using this symbol. That's basically an equal sign with the word val on top of it. This implies that they have equal underlying truth values. This symbol is not a part of the language of abstract propositions, but we're going to use it here as a meta symbol. So for example, these two propositions are equivalent. They'll give you the same underlying truth values. Therefore, we use this symbol to relate the equality of these two propositions. Now we're going to step through a number of standard equivalences. You can think of these as transformation rules, much like you'd use in algebra and calculus to transform equations to make them easier to work with or to create proofs. The first one we'll look at is commutativity. P and Q is equivalent to Q and P. Pretty straightforward. P or Q is equivalent to Q or P. And P biconditional Q is equivalent to Q biconditional P. Note that biconditional is not the same thing as equivalent. Note, however, that if P implies Q, Q does not imply P. We can verify this with the truth table. Next, we have the equivalence of associativity. In the first example, we just show that we can move the parentheses when we have a string of ands, and it means the same thing. So P and Q in parentheses and R is the same thing as P and Q and R in parentheses. The same is true with ORs. The same is also true for the biconditional. Again, note that this doesn't work with implications. Again, we prove that with the truth table. When we have associativity occur, we can just write P and Q and R instead of using these parentheses. Now let's talk about the equivalences idempotence and double negation. Idempotence basically says that if you have the same proposition connected by an and, it's the same thing as having that proposition once. The same is true with ORs. However, P implies P is not equivalent to P on its own. Also, P biconditional P is not equivalent to P. It turns out that this is equivalent to true. This is because P will always have the same truth value, therefore the value of P biconditional P is just simply always true, or a tautology. Therefore it cannot have the same value as P. Double negation is also straightforward. If you have two negation values next to a P, they can be reduced to P alone. Basically it's a double negative, like it is not that I don't like spinach means the same thing as I like spinach. Our next equivalence is adsorption. This is also known as simplification or reduction. There's a slight mistake here. This symbol is meant to represent equivalence and not a biconditional. In this example, we have P or P and Q, which is equivalent to just P alone. When we have P and P or Q, this is also equivalent to P. There are also equivalents that are basically simplifications of abstract propositions to truth constants. With inversion, we have negate true is equivalent to false, and negate false is equivalent to true. Contradiction is where we have P and not P always being equivalent to false. The excluded middle is when we have P or not P, which is always equivalent to true. Negation of P is always equivalent to if P, then false. And here are some equivalences for true-false elimination. P and true is always equivalent to P. P and false is always equivalent to false. P or true is always equivalent to true. And P or false is always equivalent to P. Take some time to make sure these make sense to you. Our next equivalence is distributivity. This is again similar to some of the stuff we've done in early algebra. Here, the and is kind of like multiplication, and the or is kind of like addition, in terms of how this rule works. So P and Q or R is equivalent to P and Q or P and R. Notice a similar pattern to this algebraic equation. Further, P or Q and R is equivalent to P or Q and P or R. Our next equivalence is called De Morgan's law. Here we have not P and Q is equivalent to not P or not Q. Also, not P or Q is equivalent to not P and not Q. Focusing on this first example, we have the truth table demonstrating their equivalence. This theme is also important to logic gates in circuitry. Now let's revisit implication and contraposition. Here we have the implication standard equivalence. If P then Q is also equivalent to not P or Q. Here we can see our first example of how we can use these equivalence rules to transform logical expressions. Starting with not P implies Q, we can apply the implication equivalence to yield double negative P or Q. Basically, using the implication, we substitute in P implies Q with its equivalent proposition, giving us double negated P or Q. We can then apply the double negation equivalence to yield P or Q alone. This means that negated P implies Q is equivalent to P or Q. Here's the equivalence for contraposition. P implies Q is equivalent to not Q implies not P. Again, note that P implies Q is not equivalent to not P implies not Q. Next we have the by implication equivalence. P biconditional Q is equivalent to P implies Q and Q implies P. The self-equivalence equivalency says P biconditional P is equivalent to true. In an earlier example, we saw self-equivalence already. This slide collects all of the equivalences we've covered so far. You're likely to find them useful to have in one place when you're trying to conduct calculations with equivalences, much like having a cheat sheet for the rules of algebra. Next up, logical calculation. By calculation here, we're talking about a logic calculus. Recall the example calculation we saw earlier, where we started with negate P implies Q and showed that it's equivalent to P or Q. This calculation was meant to answer the question, can we conclude that negate P implies Q is equivalent to P or Q? And in fact, we showed that it was. Reflexivity, where a proposition is assumed to be equivalent to itself. Symmetry, where if the proposition P is equivalent to Q, then similarly, the proposition Q is equivalent to P. And lastly, transitivity also holds, such that if P is equivalent to Q and Q is equivalent to R, then P is equivalent to R. Diving more into logic calculus, let's talk about substitution. This is the replacement of all occurrences of a letter by a formula. For example, let's replace the letter or atomic proposition P with the formula or more complex proposition Q and P, and we'll do this in the following equivalence statement. So basically, if we have this equivalence, we can make this substitution such that we get this new equivalence, where P has been replaced by Q and P. Substitution says that this is still equivalent to this. This would also be true for some substitution of Q or for both P and Q simultaneously. In other words, substitution preserves equivalence. Next, let's talk about Leibniz's rule. This is the replacement of a subformula by an equivalent subformula. For example, P implies Q is equivalent to negate P or Q. Knowing this, we can take a new formula that includes this first proposition highlighted in blue and replace it with the equivalent proposition highlighted in green to give us this new equivalent formula. Let's apply our logic calculus to prove some tautologies. Specifically, let's prove that negate P and negate P is a tautology. To prove something that's a tautology, we need to prove that it always has the value true, or that's equivalent to true. Starting with our target formula, we can apply equivalence laws to transform it. First, we apply De Morgan's equivalence, shown here on the right. This lets us transform our starting formula into this next one. And we now know that these two are also equivalent. We can now apply double negation, shown here on the right, to transform this expression to the one below it, and they're also equivalent. Lastly, we can apply the excluded middle to show that this expression is equivalent to true. At this point, we've demonstrated that our original formula is equivalent to true. Therefore, our original formula is a tautology. Here's another example. Prove that this formula is a tautology. To prove this, let's notice that there's a biconditional in this formula. Therefore, we can demonstrate that this expression is a tautology if we can show that this side of the formula is equivalent to that side of the formula. So let's try and prove that. Here we'll start with the left side of the formula. As before, we'll apply a series of equivalence rules. Note that we're using implication in concert with Leibniz's rule so that we can ignore the negate on the outside when we do this transformation. This allows us to transform our first equivalence. Next, we use the De Morgan equivalence along with the substitution rule to do our next transformation. And lastly, we apply double negation again, and this yields an equivalence with the right side of the formula. Because we've demonstrated that the left and right side of the original formula are equivalent, and they're connected in this formula by the biconditional, we know and have proved that this whole formula is a tautology. Here's another way of putting that same statement. From the fact that the left side of the formula is equivalent to the right side of the formula, it follows that this whole formula is a tautology. We've covered a lot today, so let's summarize what we've learned in propositional logic representation. We learned about the language of logic as a representation, covering atomic propositions, which are symbols with a fixed meaning that are not variables. We also learned about connectives and how they transform truthfulness across a propositional sentence. Next, we learned about truth tables, tautologies, and contradictions, and how they're important concepts for summarizing truth and falsehood across a propositional sentence. We started by dealing with a single propositional sentence at a time. Next, we learned about equivalence, and learned when separate propositions mean the same thing and can be therefore exchanged for one another. We then showed how equivalence be put into practice with logic calculus, improving a tautology. Our closing quote is, "Contrariwise," continued Tweedledee, "if it was so, it might be, and if it were so, it would be. But as it isn't, it ain't. That's logic." Please note that assignment 2 is now available. It will be due after the second module is complete. The specific due date is in the syllabus. Thank you for your attention, and I'll see you next lecture.